suppose we should get started. Hello everybody, hope your conference is going well so far. It's a good morning and people aren't too hungover. This is the Flamegraph, what you need to know to get started talk. Cool. Monitor is not refreshing.
Nice. Well, that's an interesting way to present that.
Let's try this. All right. So my name is Sean Sterling. I've been a sysadmin for 18 years. I've worked everywhere from small startups to very large enterprise companies. I currently work at a very large enterprise company doing sysadmin type things. I contribute to several open source packages, including Flamegraph. The slides for this presentation are going to be up shortly on Speaker Deck. That's where I put my slides. I'm going to also update the Linuxfest page and put the URL for that, or you can Google Sean Sterling plus Speaker Deck and you'll find me. All right, so what is my purpose? My purpose here today is to teach you guys about Flamegraph and hopefully try to get you excited about using the tool and playing with the tool. If you don't watch this show, you should totally check it out. It's called Written Word. So let's see who's awake. So how many people here have ever done an S-trace before? A couple people, okay. So I'm going to skip the rest of my poll question. All right, so no problem. A stack trace is basically what happens when either a program blows up or if you're troubleshooting and you're trying to figure out what the hell's going on. So we're going to go over just a little bit about what a stack trace is and how they work, but don't worry, this part's really short, so you don't have to sneak away. This is an example Python program where we define a function called A, which calls B. We define a function called B, which calls C. We define a function called C, which calls error, which doesn't exist. And then we begin the program by calling A. So if we run this, we're going to get a traceback. And with the traceback, you can see the order of operations here where A tried to call B, B tried to call C, C tried to call error. Error didn't exist, so we got a name error. This is a basic stack trace. This is a more advanced stack trace. In Java uses a lot of frameworks and whatnot and can get pretty crazy. So a single stack trace can take a long time to go through and figure out what's going on. And it doesn't really give you the big picture. Like you might catch a stack trace where nothing cool is going on, or if you're troubleshooting, there wasn't really a problem going on during that particular stack trace. Flamegraph lets you analyze many stack traces at once. When we're having a problem and I'll do 60 seconds of analysis, we'll get between 100,000 and 500,000 stack traces. And to go over each one individually is not realistic within normal time. As well, the stack traces that you're looking at may not be interesting and may not be indicative of the actual problem that you're having. So we need a tool to look at this amount of data, and that tool is Flamegraph. So this is our example stack trace, and for fun, we're going to say that we did 6 stack traces, 1 every second. So as you can see, main is our main function, which calls all the other programs. So we call either update stuff or do things, and then each of those can call either fix time or lookout. And every once in a while, you can see that fix time will call check clock. So that's how our example program looks like. And the Flamegraph for this example stack trace would look like this. And the first thing you need to know is that the colors are random and don't mean anything. Totally irrelevant. So that's fine. And then the names have been merged and reordered so that you can see kind of what was on the stack for however long time. And also, you and I know that 6 seconds took place during this, but we only know that because we gathered the data in looking at the Flamegraph. And then you can see the y-axis is basically your stack ancestry. So main calls either update stuff or do things, and then fix time lookout, and then it call check block. So you can make several observations from looking at just this. Knowing what I've just told you, and I realize this is weird, where do you think the majority of CPU time was taken up in looking at this flame graph?
Second row.
Sure, but on which function?
Update.
Update stuff? Sure, you could call it that. It's essentially the top edge is where CPU time is consumed, because everything else is the stack ancestry. It's what called what. So I would say the majority of CPU time here was on fixed time, although you could also say maybe it was do things because there's two samples there, but in fixed time also called check clock, which is part of the fixed time function. So that's what was majorly on the CPU during this time. Basically, as you go further and further down the stack, you can see what's calling what. This is an awesome drawing made by Agent ZH. Oh, and it's totally cut up a little bit. I really like this diagram. It really helped me figure out what was going on in a flame graph. So I modified it. Oh, neat. We're doing all sorts of. So I modified it slightly to show the individual stack traces that happened during this event, and then the grayed out bit there is one stack trace and what it would have actually looked like. That stack trace would have had, you know, my day called process emails called bug fix, and that's what it looked like. So let's take a look at an actual flame graph. This is a flame graph. It is a SVG file that you just look at in your browser. You can zoom in and zoom out. You can see at the bottom here, this will pop up and show you how many samples this was and the percentage of this. So all the samples, there's 425,000. And above here, we've got an unknown. It's unknown because I didn't have the correct debug symbols loaded for that particular item. But it's so far down in the stack ancestry that I just don't care what this is, because it's not interesting. If you look at the total of this flame graph, we've got unknown over here, and then start secondary CPU idle over here. Hopefully you can see that. I'll zoom in a little bit. So over here, this whole tower is basically what's going on when the CPU is idle. I don't care what's happening when the CPU is idle, so I can ignore all of this. And you can also grab out data in a flame graph, which is really useful, but I'm not going to bother doing that yet, but we will get to that later. So looking at this now, we know that we can ignore this whole area. And then over here, we've got, all of these are so wide that they're just spending lots of time in them, but they're not what's interesting. What's interesting is when it starts to split. So we split at doing a timer interrupt and basically handling IRQs. So that's not really interesting. That's probably hardware doing interrupts, processing, something like that. So this whole section, not interested. Like if I'm trying to solve a problem, I don't care about this whole section. So now the interesting part is this whole area over here. And even if you have no idea what this does in whatever program that you're debugging, you can kind of get a picture of what's going on by following the stacks up. So of the 3 stacks remaining here that are large enough for me to care about troubleshooting, because a lot of these are so small, they spend so little time here, I don't really care. Whereas we spent some time on this one, which is the vCPU block, VMX handle exit, and VMX vCPU run. So those are the things that I might take a look at if I wanted to troubleshoot here. And it's interesting because if you had no idea what the source code of whatever this was is, now you've got 3 entry points that you can start looking at the source code for just those parts instead of looking at the source code for a giant, huge thing. Like maybe if this was problematic, which it totally isn't, you can skip right to this function declaration in the source code and start looking at, well, what does it do? What could have caused this function to run? So it's very, very interesting to give you a big picture really fast. All right, let's go back to here. All right, this is a similar tool called kcachegrind, and this is the call map view. This is actually showing the same information, but I don't think that it's nearly as intuitive as a flame graph. But it is a very useful tool for programmers in debugging and whatnot. There's also, also this code path view, which is very interesting, but it's not really letting you know how much time is spent in each, but for programming, Kcache_grind is fantastic for debugging problems. So why should you care about Flamegraph so far? Flamegraph is great at helping you solve puzzles. Especially the complex puzzles where you're not quite sure what you're looking for. I like to call this a full stack problem. So what is a full stack problem? I'll give you a true example that happened to me last year. We are running a hypervisor stack where we have a client in a web browser that's hitting a virtual machine that's running Apache and Java, which is talking to another virtual machine on the same hypervisor, which is running MySQL. We've got dozens of these deployed that are running the same software on the same OS, with the same hardware, with configuration management. Everything is configured the same, but this one is slow. And it's not just slow, it's really slow. The customers are pissed. And so we have to figure out why this is slow. And we are running Graphite and CollectD, and we're gathering 3,000 metrics every 10 seconds, and we pore over the data, and we're looking for problems, and we just can't find anything. There's no reason for it to be slow. There's no load, there's no high load, there's no high load average, there's nothing, CPU's not busy, IO's not busy, MySQL's not busy, there's just no reason for it to be slow. The hypervisor's not busy, it doesn't have load issues, there's no IO problems anywhere to be seen. There's just no reason in the world for this to be slow. So we decide that this particular database instance might be doing something crazy that our other database instances aren't doing, and we go ahead and run strace. We run strace on the MySQL instance, and all of a sudden, the virtual machine speeds up. Which is really counterintuitive, right? When you run strace on anything, it should slow things down. But this not only speeds up, it's running at almost normal speed. So, this is really puzzling. And we can't figure out why. So we left strace turned on and redirected it to dev null for a while. But this really bothered me, and I thought,
It's probably good.
what could cause such a problem? And after thinking about it for a while, I thought of CPU speed. CPU speed is a daemon on Linux that will decrease the megahertz of your CPU clock by way of saving power. And sure enough, this virtual machine was running it. So we disabled CPU speed, and as well we took a look at the BIOS settings, and the BIOS had all of the Xeon power saving options so that, again, whenever the CPU wasn't really busy, it would underclock the CPU. So when strace was not running, it was at 1.2 gigahertz. And when strace was running, it was at 3.2 gigahertz. So okay, we disabled all of that, and then we ran our test again, and it was better. But then we ran strace on it, and it was faster again. So this was really confusing. So again, we left strace turned on, redirected to dev null, and left that for several days. The customer was happy, we were confused, and as a sysadmin, I really love the complex troubleshooting and problem solving, but this was driving me crazy. But I still loved it. And it's difficult because my manager, doesn't want me to spend hours upon hours upon hours troubleshooting something that we can just run strace on and point it to dev null and just leave it alone. But this is the type of thing that I love to figure out. So when I ran Flamegraph on a working box and on the broken box, it was obvious what the problem was, and I was able to fix it almost instantly. So let's take a look at what that looks like. Now, the display here is small, let's say. Oh, and so I'm going to try to work with it as best I can, but I'm sorry for the confusion this is likely going to cause. So we have the working one over here and the broken one over here. And just looking at it at a macro level, they're very different, right? And you can see interesting things. It doesn't matter what any of these things say. On the broken one, which is on this side, you've got these two big towers over here that are fairly thick that just don't exist over here. So that's weird. And then on the working one, this one's nice and fat over here, and this one's kind of all spiky. So at a macro level, we can already see, okay, something very different is happening on these boxes. So let's go take a look at what those things are. So the first thing I'm going to look at is the working one over here. We'll zoom in. So we do, and it doesn't matter, like at the time, I didn't know what any of this meant. Like, no idea. It's KVM debugging, and I'm not a KVM programmer, so I didn't know what these were, but you can intuitively see kind of what they are. So we see this VMX handle exit calls handle APIC access and x86, and then over here we've got handle IO. All right, so I have an idea of kind of what those functions are over here. And then when I look at this one, we do the same thing, the handle VMX exit, handle APIC access, and then, handle EPT violation, KVM MMU page fault. I'm not exactly sure what caused those, but those are definitely not good things. So we can follow up the stack here and hopefully get an idea of what caused that page fault, maybe. But that's one thing now I have a entry point for investigation, because before we had no idea what this problem was. So let's take a look at the other bits. So over here, let's make sure I'm in the right place, we've got this huge tower that just doesn't exist on the other side. So this starts at do IRQ, and then IRQ exit, and we follow this up the stack to see what's going on. So we've got a net RX action. Well, that's kind of obvious that this must be network traffic. And if you follow it up, you'll see it's a TG3 driver, but basically that's network traffic. So what's the network traffic look like on the working one? We've got the same do IRQ, IRQ exit, and then network traffic over here. So this is 500 samples. This is 2,100 samples. That's 4 times longer for network traffic. So it's clearly something's wrong in the network stack. And then over yonder a little bit, we got this other huge tower that we can just do the same thing, follow up a little bit and see, here we go, net RX, soft RQs, net RX. So again, network traffic, and then on this side, we can see the same thing. So now we have 2 entry points for troubleshooting. We've got this page fault, this page fault over here that's happening, and for some reason our network traffic on this side is taking between 4 and 5 times as long for reasons unexplained. So we take a look at the KVM network configuration, or the hypervisor, we take a look at the virtual machine network configuration, and they're identical on both boxes, on the good box and on the bad box. So it's not that. We take a look at the hypervisor network configuration, and that's also the same. And then we take a look at the KVM definition of the, come on in, it's no problem. We take a look at the KVM definition of the virtual machine, and on the good box, it's been set to virt.io, and on the bad box, the network driver is set to the RTL driver. That was the problem. So when we changed to the virt.io driver, all of a sudden, it works just as every other box was. So it was a misconfiguration at the KVM level, so defining our virtual machine, of setting the non-virt.io driver, which is not a good idea, obviously, that caused us between 4 or 5 times slower speed. And that was a really difficult problem to solve, but you could quickly get there just by looking at the Flamegraph. So let's go back to the slides. So then, after we changed that, then the page fault went away. So the question is, why the hell does running strace on the RTL drivers make them go faster? And that is a question for the KVM development team, not me. Don't. All right, so another example is CPU pinning. We've got a hypervisor that we're converting physical machines to virtual machines, and on these particular virtual machines, or on these particular physical boxes, we're running Nginx and a Java application, and we're taking those physical boxes and moving to a virtual machine. And we're trying to squeeze out every bit of performance that we can, and we've heard that CPU pinning is a way to get your performance up. So we do our initial benchmark with no CPU pinning, and it's not great, but it's okay. And then we turn on CPU pinning, and there's a lot of options for CPU pinning, like on the particular box that we're running, it's a 2 physical processor, 24 core box, like 196 gigs of RAM. And so we start off saying, all right, we're going to pin 6 CPUs to each of our 4 virtual machines on this and take a look at performance. And when we do this, performance actually goes down by 20%. So this is a really weird problem. We're like, okay, well maybe it needs 12 processors assigned to it. So we pin 12 cores to each virtual machine and try our test again. And we're slightly over provisioning on that by double essentially, but we do this for just seeing what's going to happen. And again, if it's 12 cores non-pinned, the performance is not bad. 12 cores pinned, 20% performance loss. So what's happening here? This is crazy. So we take a look at Flamegraph on both systems, working on the non-pinned and the pinned version, and it becomes obvious what the problem was. But I didn't like quite how comparing 2 Flamegraphs worked at the time. When you did it, the colors are all randomized, and it was randomized on both. This is the actual side-by-side of the working and broken boxes. And I found that I had trouble going from one side to the other side because when the colors were different, I would kind of lose my place. I'd be like, okay, I'm here and I'm following up this stack, and then I'd go to the other side and be like, okay, the colors are all weird now, and I lost my place. So I modified Flamegraph to have a consistent palette side so that the colors would be the same on both sides. I thought this was a little bit easier from going from one side to the other side, and it just made my life easier, and it was a very simple modification. So, does anybody see the problem?
Oh, that's fine.
Yeah, we see the spike. Can't
Yes.
read it.
So, good. That is the spike. That is the problem, definitely, and we'll get to that in a second. Another thing that modifying Flamegraph to have the consistent palette option was that you could run Flamegraph once with color scheme 1, and it would save the palette to a file, is what I did. And then you run Flamegraph again with a different color scheme, and then it looks up the palette map file, and for any functions that already existed, it'll use the same colors. But for any functions that doesn't exist or didn't exist in the previous run, it will use the new color scheme. So when you do that, it's really obvious where your problem is or what anything new is, and it points out where you should look. So I still wasn't quite happy enough in comparing one to another, so I'm working on another modification of Flamegraph. I hope to have it done before this conference, but the company I work for was acquired 2 months ago, so I've been not so busy on doing the transition stuff. But I'm going to get this code out there in the next week, whether it works or not, so that people can take a look at it. So this is what the new version looks like. Essentially, I've made it so you don't have to run Flamegraph twice. I run it so that you can point it at 2 different files, and we're going to show exactly how to do that in a little bit. If the color is red, that means that the difference between the first file and the second file was greater, and the darker the shade of red was the higher percentage difference that it was. If the color is blue, it's the same thing but the other way. So if the difference between the first one and the second one is less, the color is blue, and the darker shade of blue is the higher percentage difference that it is. That way you can look at either hot or cold functions that either, like if it's very dark red, that means that function was way different on the other side, or if it's very blue, it was very much less on the other side. And if it's green, that means that function only existed on your first data set, not your second data set, and I revert back to the random green colors because we have no real frame of reference on that. I think this makes comparing similar Flamegraphs very easy, very cool, so I'm really happy with that. So what was the problem? Essentially the problem was that we didn't tell the Linux kernel about the CPU topology of the CPUs. When you do so, let's go over here. Each core has a shared L3 cache, and there's some NUMA memory management as well. If you have it no pinning whatsoever, Linux will treat each core as an individual CPU with its own L2 and its own L3 cache. So you end up duplicating the same items in both L3 caches, so you're reducing your total L3 cache. As well, you can run into NUMA cache misses and all sorts of terrible things. So when you tell Linux that this core is the sibling to this other core, and there's a thread sibling here, then Linux will do the optimizations that it knows how to do to share cores, share threads, as well as you'll get the entirety of the L3 cache where it should be on the cores that it should be. And this is just an option inside your KVM configuration to say the topology of this processor has this many cores with this thread siblings and these core siblings, and that's how it works. Once you expose that to Linux, everything works great. So we went from the pinning problems we were having, the non-pinning was, or the pin version that we had before we made the topology change was 20% less performance, and then when we made the topology change, we were gaining 20% performance on top of what we had, and then some. So this is a hell of an optimization on a virtual machine. We didn't have to change a single line of code, and we gained 20% performance just by exposing the topology and pinning the CPU. That's fantastic. So let's get started. First thing you're going to need to do is install a debug info package or a debug package, which is basically the debug symbols for whatever package that you're going to use. You can do this depending on which distribution you're running, and if you're not running on one of the distributions that I've listed here, just Google debug info, package name, and you'll be off to the races. Then go and grab actual Flamegraph. Flamegraph was made by Brendan Gregg. He's one of the authors of dtrace. Fantastic. He works for Joyent, and they're doing some pretty cool stuff with Node.js. Yeah.
Netflix.
Sorry?
Netflix just recently moved.
Oh, did he? Oh,
Yeah.
Didn't know that. Cool. Good for him.
Yep.
So, if you Google for Flamegraph, you'll find it, or go to GitHub and search for Flamegraph, you'll find it. Download it. You don't need to run Flamegraph on the same CPU or on the same boxes that you're gathering your data. In fact, I recommend not doing that. I generally gather data on dozens of boxes all over the place, and then I'll pull back the data onto my desktop where I have Flamegraph installed. It doesn't really matter, you can do it wherever you want. So in order to gather data, we're going to need to use a program, and depending on what OS you're running, you're going to use different tool set. So if you're running BSD, Solaris, or Illumos, one of those guys, you're likely going to want to use dtrace, and dtrace is awesome, and that's great. But if you're in Linux, the dtrace port isn't there yet, and I would not use it. Hopefully it does catch up. I look forward to it when it does. So if you're on Linux, you're basically going to be using perf, and perf works great, or systemtap, or ktap. And which one you use really depends on your situation. If I don't know what I'm looking for and I want to gather all the debug info on everything, I use perf. If I have it nailed down to a particular PID, I'll use systemtap, although you can use perf there as well. It's a preference thing, doesn't matter. Ktap I haven't played with very much. It's kind of the new kid on the block. It looks really cool, and the next time I run into some problems, I'm absolutely going to play with Ktap. You can also use hprof on your Java stuff. And there's also a pretty cool, like if you're, I'll say, stuck in the Java world, there's a cool library called SPF4J, it's in the top corner there, that does performance monitoring, and it can do flame graphs of your Java bits. And there's also xperf for Windows. I've never used it because I'm living in a Linux world, but apparently this works pretty good, but don't take my word for it, I don't really know. So a lot of you may be thinking to yourself, is this safe for production environment? And the answer is, it depends on how you use it. So you can't run dtrace or systemtap or perf on a production system that's very busy and expect no performance hit. There's going to be a performance hit. How big of a performance hit depends on how crazy you get with your tracing. Like, you could set up a probe on every single interrupt and have that log to a file. It's not a good idea, but you can do that. And if you do that, you're going to break your system. So you've got the tool set to break your system by doing something unwise, but if you use the tool set in a sane manner, you're not really going to crash your box. I have used perf and systemtap on many critical boxes in production. My suggestion is that you test it on a production box, or on a test box. You test exactly what you're going to do in systemtap, dtrace, whatever. Run it, see if your load goes through the roof, or see if it crashes or anything like that, and then move it on to production. But you know, don't do this. And if you are going to do this, I still think it's relatively safe. I did a lot of Googling for system tap crashing on Linux, looking for horror stories of people blowing up their production box. Red Hat ended the preview for system tap in 2009, and I haven't been able to even find anybody through an hour of searching saying, system tap broke my box when I ran this, since 2009. Pre-2009, you will find people saying, oh my god, system tap crashed my box doing this. So don't take my word for it, Google it for yourself, take a look, try it on a test box, then use it in production. All right, back to business. Once you gather your actual data, depending on how you gathered it, you may need to run stack collapse. Stack collapse is a Perl script that will take your trace perf system tap output and put it into a nicer form. It's easier to process. And it's great because you can grep things out or in if you really want to combine some stuff and do some crazy things. It's just a simple Perl script. Take a look at the folded file at what it outputs if you want to. Very cool. And I'm gonna show how that works shortly. So this is a regular Flamegraph and the command used to get there. So we gathered data and then we took the broken file, piped it into Flamegraph, and then redirected the output into an SVG file. You fire that up in your browser, it's gonna look like this. There's also a hash algorithm that uses a hash, if you can believe, that will use the hash to do your colors based on the name of the function that it's tracing. I use this actually came out after the consistent palette option that I made was written, but even using this, the colors don't vary enough for me. I actually came to prefer the very wild random colors, but you might like this mode and that might work for you, and that could be great. This is the consistent palette option, and basically we've got one on one side and then a broken one on the other side, just using the same palette. Very simple. This is using the consistent palette option to make colors go all crazy. So what we do is we delete the palette map or copy it somewhere else, whatever, because that's where all your colors are stored. And then you run the first one with the consistent palette option, and then the second one changing your color scheme to a different color scheme, of which there's a couple. Like there's a memory color scheme, there's an IO color scheme, and there's the regular color scheme. So that's how you'd use that if you wanted to. So if that was all that Flamegraph could do, it would be a pretty cool tool already. I would already be really happy, and this would be a great addition to my sysadmin power user programmer toolset. But it can do so much more cool things. Off CPU Flamegraphs are a thing, and what that is actually first let's back off a little bit. If I was to tell you that I had 80% CPU time, that's not really a thing. Your CPU is a simple state machine. Either it is processing or it is not processing, right? It's either on or it's off. When I tell you I have 80% CPU time, that's a function over time. That means in the last 1 minute, in the last 5 minutes, 15 minutes, whatever, my CPU had stuff to do 80% of the time, right? Off CPU is essentially when you have context switched off the CPU. So your CPU is waiting for something. It's waiting for disk I/O, maybe network I/O, or maybe there's an interrupt or a page fault, memory mapping, something like that. Looking at what you're waiting for in the off CPU is sometimes the interesting bit, and you want to take a look at that. So as a reminder, to look at the software stack on a Linux box or Unix box, whatever. If you're writing in a script language, there's a script VM, which heads on over to user space, which heads on over to your kernel. And if you're already a dtrace system tap, perf, ktap wizard, you already know how you can do traces at every single one of these levels, right? So if you want to capture only kernel events, you can do so, or only user space events, you can do so. Or if you just want to capture at the script VM, you can do that as well, and that's super cool. So we're going to come back to the off CPU in a few seconds and do a little bit more on this. This is Agent ZH. I'm not going to butcher his real name. He is a Flamegraph contributor, and he's the guy that did that cool Flamegraph drawing that I totally stole earlier, but I gave full credit so I don't feel guilty. He has a really cool program called Nginx System Tap Toolkit. Now you don't need Nginx, you don't need to know about Nginx or how Nginx works, you need to know nothing about it. This is just there's several tools built into this that you can use to do all sorts of weird and wonderful things. The first of which is called check debug info, and it pretty much does what it sounds. You run check debug info against a PID, and it will tell you if there's any debug info built into the program. Like if you compile a program with debug symbols there, then this will tell you that the debug symbols are there. It doesn't tell you, like if you're running RPM or apt and you install the debug package, it won't tell you that yes, you have the debug info package installed for whatever that is, which you can also sort of get if you just run LDD, but LDD is not going to tell you if the debug symbols are compiled in, so it's kind of a handy tool to see both sides of the equation. So in this example here, I already have the bash. I decided I'm going to do some tracing on bash. I decided I also want to get the LD function or the ld.so. So I wasn't sure which package that was, so I just did a rpmqf, which tells me, hey, that's glibc, and then I get the glibc debug info, and now I can debug that. I tend to only install one debug info at a time, and then run it, gather the data, and then I'll install another one, because you really only care about, like, the bottom three things on your stack ancestry don't really matter. It's more the middle to top part of what's going on in the stack that's interesting. Another one of his tools is called SampleBT. SampleBT lets you run against a PID, and it runs system tap very simply, and you can gather either the kernel calls, the userland calls, and set a timer very, very simply. You can do this in perf, but perf is kind of more of a gather everything tool, or at least that's how I use it. Perf can definitely, you can point it at one PID if you want to, and you can specify only kernel calls or userland calls as well. But this would be getting your feet wet with system tap, which is a more powerful tool for Linux. Like you can set filters and all sorts of fun stuff.
When you said one debug info at a time, do you mean one package?
Yes, I did. Sorry about that.
And does he do anything on dtrace?
He does not do anything on dtrace. He is in a Linux world. Yeah. So this is using SampleBT, pointing it at a PID. The -t is just how much time to do it for. The -k is for kernel, the -u is for user. You can do -k and u for gathering both at the same time. And again, slides, they'll be available, I promise. So this is using SampleBT on a running bash session, gathering just the kernel calls. And then we run stack collapse and Flamegraph, and then lo and behold, here's our lovely Flamegraph of what's going on. This is the same bash session with the userland calls turned on. And as you can see, that's a bit of a nightmare to look at, right? Like, I don't know if you can see, but it's mostly execute commands, and we don't really care about that, or maybe you do, maybe you don't. This is the same thing with userland and kernel calls turned on, so you can see kind of the nightmare mess that this is. So one of the great things about once you get it into the stack collapse bit is that you can grep things out. So what do? We grep out execute command. And now we've got a more functional Flamegraph, and we can kind of figure out what's going on besides it launching a zillion other sub-processes to do whatever it needs to do. That's a pretty slick thing that you can do. To go from this, you know, to, oh, neat, we went the other way. To go from this to this, that's fantastic. And you can grep out all sorts of other interesting things, like sometimes you'll see some CPU idle stuff that you don't care about, and you can grep that out, and then you're just looking at what's important in your Flamegraph, and that's really nice. Another interesting thing about the SampleBT is you can pass the -d flag, and that's going to spit out the system tap script that it uses. And you might not care about that, but as you progress further towards becoming a system tap ninja, this will be really cool to go in and play with the actual system tap script that was generated for this. So You don't have to do it, but it's a neat tool to help you become a system tap master. So there's also sample BT off CPU, and as you can imagine, this does the off CPU tracing for such things. This is a really good tool to figure out what's going on a particular PID that you think is waiting. So like, if you have something that's at a high percent user on your system or a high percent system, using either of these tools is great, because then you can grab the kernel land stuff or the user land stuff, whichever one it is that's high, then this will allow you to troubleshoot and figure out what's going on. So the usage for this is pretty much just like the sample BT, pretty much exactly the same, and you can also do the -D as well to get the system tap spit out there. And for this one, it's actually really cool. You should, if you want to take a look at something neat, take a look at that. So this is the same Flamegraph for the off CPU for the same bash session, and it's very different, as you can see, like what bash, the process bash is waiting for. It isn't really much. There's a lot of like waiting for a key input and that kind of thing. Another one of the tools is called sample BT VFS, and this is for hitting the Linux virtual file system. And this can be a little bit confusing because the VFS is file I/O and not disk I/O. So your read cache can absorb a lot of your reads. So if you think, well, geez, I should be doing like 1,000 IOPS here, but if whatever that file is in your disk cache or your read cache, you won't see them. And so it can get a little confusing, but you can set up a dtrace perk whatever on the actual file I/O if you want to, not with this tool. So this tool will let you sample the I/O or the I/O latency as seen by the Linux VFS. And this is an advanced topic, by the way. Like, you probably won't need to get into this unless you're troubleshooting something particularly weird, but it's great. It's a great tool to have that you can do this easily with just this tiny little script. So this is a strategy I like to use, even if you wrote the program yourself. Rather than shoving a whole bunch of print statements and or firing up GDB, although firing up GDB is cool too, fire it up in Flamegraph and take a look at what your own program looks like. So debug it like you stole it. Grab it, load it into Flamegraph, and be like, geez, I didn't know this function was taking up this much CPU time and this much I/O. That's really weird. I'm going to have to take a look at that and find out why. It lets you look at some interesting bits. But if you're running if you want to do a Perl script easily and you want to take a look at your Perl VM calls, the best way to do it currently, according to me, is to, again, go visit Agent ZH's page and grab his Perl System Tap Toolkit. And this is going to allow you to run a Perl land Flamegraph so you can actually see your Perl calls and how they look inside of Flamegraph, which is super cool. If you use Python or Ruby or whatever other scripting language that makes you happy, pretty much you're stuck in a dtrace world right now. And if you live in Linux land, that's difficult. That means you got to fire up a BSD box or Solaris or Lumos, whatever, and do it there. There doesn't seem to be a existing system tap script ready-made for you to do that. I have delusions of stealing the Perl version from Agent ZH and modifying it to do Python, but I haven't run into a unruly Python script because I'm a Python guy. I haven't needed to do it yet, but I'm anxious at the opportunity to do so. Or I might do it with Puppet and KTAP just as a learning experience, because Puppet has some slow bits. I'm a Puppet guy. And I'd like to see what those slow bits are and then, write an email saying you guys should take a look at this. So what else is there that Flamegraph can do? This is going to be hard without my notes, but here we go. Flamegraph can be used to find memory leaks, which is really cool. You can use it to, you can put a trace on page faults, on memory maps, on all sorts of interesting, and you can basically have it so that it does bytes. So like you could put a trace on malloc or dealloc and set it to, instead of its sample count, you can set it to byte count, so you can see every single malloc and every single free. And that way, if the graph doesn't look perfect, you know that there's a memory leak, something's not getting freed, or you're mallocing too many things. You can basically tie it into any type of I/O or I/O latency, so your network, your disk, your whatever, all that will. You can generate a Flamegraph and take a look, help you troubleshoot. Basically, it's a really cool tool for troubleshooting the odd problems. So, the next time you run into some weird WTF stuff, throw on a dtrace, system tap, ktap, whatever, and then fire up a Flamegraph and give it a try. And that's all I got. So, thank you. And any questions?
You tried graphite?
Oh yes, very different tool.
Yeah.
Graphite is more of a, I use graphite and CollectD, although I'm looking into switching to Diamond, which is a Python kind of CollectD equivalent-ish. For all of my systems, I basically gather 1,000 metrics every 10 seconds using graphite, and if it's a SQL server, we do another 3,000 on top of that using, I actually contributed a plugin to CollectD that hasn't got merged yet after 2 years. I don't know, merges are slow there for reasons unexplained. So if you monitor MySQL and you use CollectD, grab my plugin. There's sitting in the merge request or search on Sterling CollectD, you'll find it. Because gathering all that data is fantastic. But this is quite a bit different world. This is not program statistics gathering. This is program stack tracing and figuring out what exactly the program is doing and looking through the ancestry of that to figure out, okay, why is this slow? It's slow because it's waiting for an I/O restriction that you forgot you turned on the file system or something like that. And it just makes it so obvious, and a tool for basically analyzing thousands upon thousands of stack traces instead of looking at an individual stack trace. Sure, Amy.
Have you had to roll your own metrics collection for things that are not prepackaged or waiting on a commit from, CollectD, etc.?
Yes.
What do you use for that? I've done it in Bash or in Shell just to grab something needed from the kernel and it's like syscontrol, etc.
Yeah.
Chuck it on over.
The developers for the company I work for, they have their own Java stuff that Java gathers a ton of stuff as well. I've written some stuff. I'm the author of Graphios, which takes it takes Nagios perf data and shoves that into Graphite. That's on GitHub if you want to check that out. I've written several other Python utilities that just take whatever and shoves that into Graphite.
Well, examples where you're grabbing it from.
Oh, everything from, we have a weird plugin for Nagios that anybody can just echo something to a file, and if that file exists, it'll grab it and shunt that into Graphite. Some Proxys stuff, like everything. Put it into Graphite so that you can figure it out later. Any more questions?